Welcome to another video for Stat 420. In this video we're going to continue looking at multiple linear regression, but now getting into hypothesis testing and confidence intervals and prediction intervals, working with the multiple linear regression model. So we talked about in the previous video how the standardized beta hat j's are going to follow a t-distribution. So if we're using the standard error of beta hat j, kind of that estimate of the standard deviation of beta hat j in this formula, then these standardized values are going to follow a t-distribution. Therefore, we could use a t-test to test kind of a null hypothesized plugin for beta j. So for example, probably the most common beta j that we'd plug in here would be 0. So beta j equals 0 would basically mean that this predictor is not adding anything to this model. Therefore, if we have evidence that we're really far away from that, if our beta hat j is sufficiently far away, if it's several standard errors away from that, then it probably means that we have enough evidence that beta j is not 0, that it is some value. Therefore, this predictor does kind of add something to this model. It does have a linear relationship on top of the other predictors that we already have. So I'll kind of draw a picture here just as a reminder. There exists a distribution of beta hat j's where j could be any predictor. It could be 0, it could be 1, 2, 3, 4, doesn't really matter. But there is this distribution centered around this true beta j value, whatever it is that we're looking at. Again, sorry, sometimes I do pretty well with these normal distributions. Sometimes they look a little bit sad. This one's a little sad. And we don't know where our beta hat j is. We just know it's around whatever that beta j value is. So if, let's say, our null hypothesis is that beta j equals 0, then right? This is 0. And then we see how far away our beta hat j is, where it falls in the distribution. So basically what we do is we say, okay, let's assume it's 0. So let's put 0 in the middle. And our beta hat j, oh, it's actually way, way over here, right? We'll just say, right? So here's our beta hat j. So then we're basically finding how often we get a value this far away or farther by random chance. So we can kind of, if we're doing a two-sided test, which we typically are going to do, we're going to shade both sides of this. Basically, how often are we going to get a beta hat j this far or farther by random chance if beta j really is 0? That's the center of this t-distribution. And that's going to be our p-value for this test. Okay. So one thing that changes here, this is where it gets a little bit tricky, and hypothesis tests are a little bit hard to interpret in a multiple regression context, and that's because we're basically judging the significance of this predictor given that this other predictor is already in the model and being used. So even though these might individually be significant predictors, right? So like we have weight as a predictor, we have year as a predictor, and we could run solo models and say each of these as a solo predictor is significant, that we have evidence that there is at least some kind of relationship going on here. However, it's possible that if we have both of them in the model, that we don't really need both. In other words, that it could just be that weight and model year have some correlation between them on their own, and that it's really just kind of one of these things that's really providing the predictive power, and the other is just only providing as much predictive power as it kind of shares with the other predictor. So maybe if I can kind of come up with an example here, let's say that we're talking about productivity or something like that. So we're trying to measure people's productivity. And so maybe one predictor I use would be maybe something kind of related to, like, we'll just say intelligence, something related to intelligence. So maybe like one is kind of like your high school GPA and one is kind of like your, we'll just say like your ACT score. This probably sounds like a terrible model. But the thing is, if I pick two predictors that are really correlated with one another, then I don't really need both of them in the model. And even though they might as solo predictors have some significance, if I look at both of them, I find that there's a lot of redundancy, and all of a sudden one doesn't add anything when the other is already there. So that's what's going to go on here with multiple regression that we want to kind of test, is we're saying, how do we have evidence for significance with this predictor, given that we already have this other one in the model too? So if we have a two-predictor model, we can kind of think about the null and alternative hypothesis like this. So if we're testing beta 1, whether it has significance, then our null hypothesis is that this model is, fine, it's plausible, in comparison to this one is really not buying us anything. So like if we add this beta 1 term, this could just be some random chance variation as opposed to some meaningful predictive power being added. So I'm going to kind of write out in words the null hypothesis for a multiple regression. I'm going to say, so if we're looking at weight and model year, so a car's weight has no linear relationship with MPG after, I'm going to say after adjusting for model year. And I could phrase this a couple different ways. We could also say when we also have model year, or when controlling, well, actually, I don't think I'd say when controlling for model year necessarily. But after adjusting for model year is just kind of giving the suggestion of, I already had this other predictor. I'm looking to see if this adds anything more, if there's a linear relationship after already having this other predictor in the model. The alternative is going to be something like, and I wrote HA, H1, either one of those works. All the same word, but has a linear relationship. With MPG, again, after adjusting for model year. Okay, so solo, we don't have to say that. With multiple, we do have to say, if we have all these other predictors already, is it adding anything? Okay, so we ran a hypothesis test with both of these predictors, and it looks like even after adjusting for the other one, the other predictor is still giving a lot of evidence for some linear relationship. So our conclusions here in both cases are that weight seems to have a linear relationship with MPG even after adjusting for the car's year, and vice versa. Car's year has a linear relationship with MPG even after adjusting for weight. And if our p-value is not so low, maybe if it, like above that 5% threshold is something that we commonly use, if we saw a p-value that's a little bit higher, then we would just say we don't have enough evidence. We're not concluding that it doesn't. We're just saying that what we saw could be explained by random chance. It wasn't enough for us to say confidently that there's a relationship to note here. Okay, so we can also do confidence intervals for beta hat J, and we can kind of use our standard error. We can use our t-distribution again. So as long as we have a t-critical value to plug in based on the degrees of freedom that we have, the confidence level we're interested in having, we can calculate how many standard errors we want to kind of extend out from our beta hat J estimate, or our estimate for beta J, which is beta hat J. Now, I do want to mention here this n minus p value. So our degrees of freedom now is not going to be n minus 1 necessarily, or n minus 2. It's going to be n minus p, where p is the number of parameters that we're working with in this model. So let me just kind of make a note here. Right, so if we have beta naught, beta 1, and beta 2, p is going to equal 3. So for each parameter estimate involved in this equation, there's what's called a loss of degree of freedom, which is just kind of a shorthand way of saying we're estimating an additional thing that's going to weaken this estimate. The more things I estimate, the more parameters I'm estimating, the more iffy this estimate's going to get of the true standard deviation of beta hat j. Now, it's still going to follow a t-distribution. It's just going to follow a t-distribution with less degrees of freedom, meaning that there's going to be a little bit, it's going to be a little bit more of an error correction, right? So I think you've seen a picture by this point that, you know, if, let's just say that a normal distribution looks like this, something like that. I mean, again, not my greatest work, but it works. Then a t-distribution with, say, 20 degrees of freedom, let's say df equals 20 is going to be in red here, is going to be a little bit fatter tail, not quite as, ooh, no, let's try this again. You know, I'm going to, goodness, I need to just redo all of this. Okay, bear with me, guys. This is hard. Here's a normal distribution. This is good. Okay, nice thin tails. That's what I'm looking for. Okay, let's do a t-distribution with degrees of freedom equals 20. So this one's definitely going to have some noticeable error correction, but not a ton. It's going to be a little bit fatter over here, not quite getting there, and then again just a little bit more like this. And then let's say that I have one with even smaller, like maybe degrees of freedom equals 8. This is going to be even more noticeable. That's just not going to quite get there, and that's going to be kind of a fatter distribution again. Now this is very like approximate, but the idea here is that the tails get bigger. So there's more chances that I'm going to be out here, less chance that I'm going to be in here. So every time there's a parameter estimate, that degrees of freedom goes down, and I have a little bit more, you know, estimation going on here, and I need to account for that in the t-distribution that I'm approximating to. Okay? So we're going to calculate a confidence interval. Again, we've seen this general template before, but the math is not super important as much as the fact that we can just use R to do this for us. So we could do a confidence interval of our model with a particular confidence level of our choice. And in this case, it's just going to do it for all the parameters. So I can just do a confidence interval, and I get one for the intercept, I get one for predictor 1, I get one for predictor 2. And that's great. And notice that, I'll just kind of make a connection here. Since my p-values are both really, really low for these variables, notice that they don't straddle 0 in these confidence intervals, right? So if my p-values were above 1%, and I was making 99% confidence intervals, then I would expect these intervals to straddle 0, or whatever, you know, whatever null hypothesized parameter I was using. When that's not the case, when the p-value is really low, then our confidence interval should be completely above 1 or completely below 1. So that connection should kind of go together there. We can also make confidence intervals for the mean of y given a particular x. So it's not just doing confidence intervals for beta naught, beta 1, beta 2, but a confidence interval for the mean value of our response at a particular value for x. Again, there's kind of some mathematical setup that we're not going to worry about deriving as much as we just like that it exists and that somebody has done this. And so the standard error for y hat, so basically the standard error for the mean value of y at a particular x value is going to be represented by this equation. So it's going to be, again, the standard deviation of our residuals times the square root of this expression right here. So if you wanted to make a confidence interval for a mean of y given x, we could use this expression right here. Again, it's very easy to do with code. So this is an example, by the way, that is doing a confidence interval for the mean of y at 2 different x values. So one is at weight is 3,500, year 76. The other is weight is 5,000, year is 81. So notice here that we do have 2 plugins. If we have 2 predictors, then we do have to note what both of them are in the confidence interval expression. And if we want to do more than 1 point, so instead of just doing 1 point, we're doing 2 points. So 2 values for each predictor now. So we're going to plug that into the predict function now. We're going to do a confidence interval at the confidence level of our choice. And in this case, I could also just like directly plug this in here, by the way, right? So I don't necessarily have to set this up ahead of time. If I wanted to just like plug all of this in here, I could, or I could define it ahead of time if it's a little bit long and I don't want this to get really messy when I write the predict function. And again, we can see this is a 99% confidence interval. So what we would say is that we're 99% confident that the mean of y at this point and this point should be between these two values and these two values. So again, this is weight equals 3,500, year equals 1976. The second one is the prediction for when weight equals 5,000 and year is 1981. All right. Now, this is something that I think is just really interesting and something that you may not have thought about, and that is multidimensional extrapolations. We've talked about extrapolation before, and that is when we're making predictions for the response for a range of x that we have not observed. So if you think about weights that we've observed and you think about years that we've observed, we should be careful making predictions when we're outside that range. Now, this is where it gets a little bit tricky. I might observe, I'm looking for cars of a weight of 5,000, well, my head is in the way again as usual. And I'm looking at this range and saying, oh, well, look, I have observations of cars from about 1,500 to a little over 5,000, so that's safe. I had that. I'm also going to notice I'm looking for cars of year 1981. Again, that should be pretty safe. I have a pretty wide range of car years here. However, I don't have observations that really fit this sector. So even though it individually is in this range, and it's individually in this range, it's kind of outside the multidimensional range that I have here. So we want to be careful of this kind of multidimensional extrapolation, that we're not just checking individual variables, that we're checking cohesively, do I have values at around, that range for both variables at the same time, or for as many variables as I'm looking at. And so that might be kind of tricky to do if we get outside of 2 dimensions. Obviously, I can make a 2D plot and check this with 2. If I have more predictors, that gets a lot harder. But we just want to kind of put that on our radar, that we do still want to be cautious of that. All right, and the last thing in this video is just a note about prediction intervals. So again, a prediction interval is when I'm looking for, like say a 99% prediction interval is the boundary such that 99% of the data should fall in that range at a given x value. So a confidence interval is estimating a parameter. A prediction interval is measuring or predicting kind of the range of individual data points. So if I have kind of a scatter plot here, make it a little bit wider. This is like a slightly too neat scatter plot. Like I feel like we never get data that's like so cleanly inside this range. Then I'm going to have a best fit line, right? Maybe it's going to look something like this. Hopefully slightly straighter than that. And I can create a 99% confidence interval for the mean of y at any given x, and that's going to be kind of in this range, around the line, right? So depending on how much data I have, I might be pretty confident of where the mean of y is going to be. And so this is going to be kind of this very narrow range around my line. Whereas a prediction interval is going to be capturing that percent of the data at any given point, right? So prediction interval is going to be much wider. So this is a prediction interval. This is a confidence interval. Now, this is 2-dimensional. This is just one predictor, one response. We're now talking about prediction intervals in more than 2 dimensions. So it's a little bit harder to visualize, but it's kind of that same idea. Is if we're doing if we have 2 predictors, then it's not just kind of this interval around a line, it's an interval around a plane if it's 2 predictors. And if it's more than that, then it's some other more complicated geometry going on there. However, we can still, use some math to represent the standard error of our estimate for y at a given x. So not necessarily not an estimate for the mean of y now, but an estimate for just y in general. So we have a standard error. The only thing that's different from the standard error for the mean of y is that we just have a 1 kind of added into that square root expression. Otherwise, I think everything else should be exactly the same there. But again, we'll just kind of make a note of this is really easy to do on R. We can use the predict function one more time. The difference is that we're just going to say interval equals prediction instead of interval equals confidence, and we can get a prediction interval around the points of our choice. So they're not really shown here, but we kind of set up that same new cars data frame where we have some data points. We're plugging those in and getting a prediction interval around those x values.